Okay, in this lesson we're going to talk about simple harmonic motion. So we're going to look at this interactive figure for just a minute to show what that means. Here we have a graph that's graphing time and length. Remember, S was our arc length when we talked about this in trig. So we have the arc length as a function of time. Over here on the right hand side I have a spring with some sort of weighted box or a mass at the bottom. Okay. Over here on the left, I have some slider bars, so I can change the size or the weight of my box over here. This spring constant, it just happens to be particular for this type of for any type of spring. We're not going to worry about it. Amplitude. Okay, notice right here we have equilibrium, and if I wanted my amplitude, in other words, my coil sat 10 centimeters above equilibrium, okay, or maybe I want to pull my spring down, and at time of 0 I want my spring, it's going to start here at 15 centimeters below equilibrium. Okay, well, let's watch what happens if we were to pull this spring down and then all of a sudden let it go and start counting with time. What happens? Here we have the spring bouncing back and forth, and look what it's doing. It's creating a trig function. Notice here this is a cosine function because my spring started at below my equilibrium or below the 0 point. Okay, I could have put my spring, let's reset this, I could put my spring up here. Let's push play. Okay, you can see how it's changing the function there. All right. Okay, so all of this is just to say that a harmonic motion would exist in, let's say, this example right here of a spring. We could have a pendulum. We can have all sorts of things that create harmonic motion, and that's what this lesson is about. Off to the notes. Simple harmonic motion. Simple harmonic motion is going to be defined as, you can find simple harmonic motion using arc length as a function of time, and this trig function right here where we have amplitude times some cosine. Okay, then in here it's the cosine of the angular speed and time. Remember that this was our angular speed. Okay, remember that this is angular speed, and angular speed is actually taking the place of what we used to have for b. So instead of a b variable right here, instead of b, we have angular speed. And this is true, okay, whatever we're talking about as far as harmonic motion is considered, we're talking about either using a cosine or a sine function, and it really just depends on what we're starting out as. A few more things to define here. The period, which is going to be the time it takes, okay, is one complete cycle. The period is, we can find the period by taking 2 pi over angular speed, which makes sense because in the previous sections we've been doing 2 pi over b. Now we're doing 2 pi over w. And the frequency, that's the number of cycles per unit of time. Okay, the frequency would be the oscillations per unit time, or the number of cycles, is basically just the reciprocal of the period. So it would be the angular speed over 2 pi. All right, let's take that information and let's jump into an example that we have. First one we're going to look at talks about modeling the motion of a spring. Okay, so I drew myself a picture that's going to represent this example. It says, okay, suppose we have an object that's attached to a coiled spring and it's pulled down 5 inches from the equilibrium position. Okay, so we're pulling it down to 5 inches, and then all of a sudden we're going to release it. Okay, so it starts out at 5 inches below equilibrium, then we're going to release it. And the time it takes for one complete oscillation, so it would go up and down or whatever, would be 4 seconds. So we're going to figure out how to solve this type of an equation. So what do we know to begin with? Okay, we want to be able to, in this part right here, give an equation that models the position at time t. So we need to first decide what type of an equation are we looking at. Remember that we had both a sine option and a cosine option. They're both the same equation, but we had sine and we had a cosine function. Now, right here it says that the spring is pulled down a distance of 5 inches from the equilibrium position and then released. In other words, we're going to pull it all the way in the down position and then we're going to release it. That right there, because it's pulled down, that right there in that sentence tells me that I'm looking at a cosine function. So we have s of t equals a cosine angular speed t. Okay, so we needed that information right there to know we were talking about cosine. The next thing that I know from this that I'm given is that it's pulled down a distance of 5 inches. So a, in this case, would be -5. We also know that for one complete oscillation, it's 4 seconds. In other words, the period here would be 4 seconds. Okay, so, and I'm trying to create an equation where this variable t is the only variable in it. So I know what a is. I need to know what angular speed is, but I'm given the period. So what we can do, okay, so in other words, I'm trying to figure out what the angular speed is. So we're going to use what we know about the period in order to calculate W. Okay, we know that 2 pi W is the period. We also know that the period is 4 seconds. So we're basically setting it up like this so I can solve for W. Cross multiply, I get 2 pi is 4W, and then I end up with W equals 2, because I'm going to divide by 4 pi over 2. Okay, so now I know what W is, I know what A is, I can write the equation. So I'm going to come in and I'm going to fill in the equation here. S of t equals -5. Remember, we're starting in the down position. Cosine pi over 2 t. Alright, so that is the equation that models this information I'm looking for. The next part says, well, okay, determine what the position is at t equals 1.5 seconds. That's pretty straightforward. We're just going to come in and we're going to take our equation, plug in 1.5 for t, and solve. So we have -5 cosine pi over 2 times 1.5. And then we're just going to plug this into our calculators and get an answer. When you do that, you should find out that the position, or S, is approximately, when we plug it in our calculators, 3.54 inches. And if we were asked, we could say that the position of the spring was above the equilibrium. Position above equilibrium, because 3.5 is greater than 0. Since it's greater than 0, we know we're above that. Position. Now the last part of the question says I need to find the frequency. Well, if I know what the period is equal to 4. I know that the frequency is the reciprocal of the period, so it's 1/4, because it's the reciprocal of the period. Okay, pretty straightforward. The only thing about that is you had to figure out what you were doing. You had to figure out which function or which equation you were going to use, which simple harmonic equation you were going to use, whether it was cosine or sine. All right, let's look at one more as far as spring motion is concerned. Okay, this time it says that the height obtained attained by a weight that's attached to a spring set in motion is given by this equation right here after t seconds. And I am wanting to find the maximum height that the weight rises above the equilibrium position. Okay, I'm wanting to find the maximum height that it rises above the equilibrium position. Well, let's take the equation first of all. We know that when we're talking about the maximum height or the minimum height, right, we have a function that's doing this right here. Whether it's the sine or the cosine, it doesn't matter, but we know we have peaks and valleys. And at our peak and at our valley, we know that that is the amplitude. So in other words, if I were looking at the equation that they gave me, the amplitude of this equation is 4. So the maximum height that this weight rises above the equilibrium is 4 inches. Now, when does the weight first reach the maximum height? So when is it going to reach that first maximum height? Well, wouldn't that be the period? In other words, we're going to use the period in order to figure out where that maximum height is. Let's take for a second, I'm going to erase my squiggle here. We know we're talking about cosine. We know we have some function that's going to do this right here. Okay? Now, if I want to know the first time it reaches this maximum height right here, then that's going to be halfway in between one complete period. Okay? Okay, so let's go back and let's figure out what the period is of this function anyway. The period is supposed to be 2 pi over 8 pi, or 1/4. Okay? So if the period is 1/4, and I want to know what the maximum height is, okay, when is the first time it reaches this maximum height, then I'm really looking at halfway in between 0 and 1/4. So in other words, it would be at 1/8 second. Because remember, we're talking about a period is a function of time. Okay, so it's 1/8 of a second because the maximum height is half of the period, because the maximum height is half the period. Period. All right, and now what is the frequency and the period? Well, we already know what the period is because we said that the period up here was 1/4 seconds. So if the period is 1/4, then the frequency would be the reciprocal, which would be 4. And the frequency we've said is the number of cycles per time, so cycles per second. Okay? All right, so I hope that helps explain the spring motion